Okay, so we are doing the following today. Basically, we're finishing up 10.1, so on Thursday I'll be talking about 10.2. Now, there's not much left to talk about except for what are maxima, minima, and random other critical points. So I'll go ahead and let you read this for just 1 second before I get talking. Okay, now that I've done that, let's go ahead and talk through it. A relative maxima is going to just be a point that's higher than anything around it. So when I'm thinking relative maxima, I'm literally thinking like a peak. A relative minima is going to be a point that's lower than anything around it. So I'm actually going to keep these two pictures. There's a maxima and there's a relative minima. Now we've already kind of discussed this. Notice that at the maxima, you go from increasing to decreasing. So we'll say that a relative maxima will be a critical point because, hey, look, its derivative equals 0, its horizontal tangent line. It's going to be a critical point where you go from increasing to decreasing. Similarly, a relative minima will be a critical point. Look at that, flat tangent line, horizontal tangent. But with a relative minima, you're going to go from decreasing up to increasing. So you're kind of seeing how we're going to find these relative maxes and mins. We're going to probably do our number line process, and then we're just going to kind of call out, hey, am I going from increasing to decreasing or decreasing to increasing? Now, two other points that we could talk about would be, what if I go from increasing to increasing or from decreasing to decreasing? That kind of knocks out all possibilities. So for instance, right here and right here where my function goes flat for just a second would be critical points. Those would be points where my derivative equals 0. But notice on the left, I'm increasing, and on the right, I'm still increasing, and vice versa. On this side, I'm decreasing, and I'm still decreasing. This is what we're going to call horizontal points of inflection. So that's what this last chapter, or that third paragraph is about. If you ever go increasing to increasing or decreasing to decreasing, and you're actually a point on your graph, which is important, then yeah, we're going to call you a horizontal point of inflection. And this is what you look like in this last column down here. Now what we're going to do for the following problems is we're literally just going to be finding my relative maxima, minima, horizontal points of inflection, as well as intervals of increase and decrease. So I'll leave this picture up here. I think it might be useful. But let's go ahead and start with the function f of x equals x cubed minus 3x. Now this is one that we've already done a couple times, so you should actually have a number line in your book. But remember, to get a number line, we first off find the derivative, since we're wanting to know about increasing and decreasing. And then we find where the derivative either equals 0 or does not exist. It turns out, since it's a nice looking function, you're never dividing by 0, it will never not exist, so we just set it equal to 0, which is typically what you'll do. Add over to the 3 to get 3x squared equals 3. Divide by 3 to get x squared equals 1, and then square root both sides to get plus or minus. Remember the plus or minus here. And boom, these are my critical points. In my head, what I should be thinking is that plus minus 1 are potential mins and maxes. So these are my blue points up here, plus or minus 1. Great, now we go to a number line. Throw up all your critical points on the number line, so -1 and +1. I like to draw little borders. I guess I'll do it solid because my drawboard app doesn't do great with dotted lines. And then I take test points for each little section. So over here, I'm going to take a random point from anywhere in here. I'm going to pick -2 because it's a nice number. Now I take a point from anywhere in here, literally could be anything. I'm going to take 0 because it's a nice point. And then take a point anywhere from over here, and I'm going to pick 2. Now we're testing these in the derivative. What I want to know is, am I increasing here or am I decreasing here? So what I need to do is to plug my test points into the derivative. So f prime of 2, negative 2, f prime of 0, and f prime of positive 2 is what I'll do. Recall that my derivative is 3x squared minus 3, so when I plug in negative 2, I'll get positive 9. When I plug in 0, I'll get negative 3, and when I plug in positive 2, I'll still get positive 9. So that I look like this. Now, sometimes it's helpful to actually just draw out what the function is doing with maybe arrows. So something that I've seen that's helpful is where there's a plus, meaning increase, draw an upward looking arrow. Whereas a minus, meaning decreasing, draw a downward moving arrow, and you guessed it, another positive upward arrow. It's kind of a nice visualization of what you're going to be writing up for your answer. So there's the process in total. Now, last but not least, you're just going to be interpreting. So what we could do, based on that graph right here, well, we could first off say where we're increasing on, kind of like last time. We're going to be increasing wherever you see a positive. So notice we're increasing kind of from this solid line right here all the way to negative infinity. So we're increasing from negative infinity up to that solid line, which occurred at negative 1. We're also increasing from this solid line right here all the way up to positive infinity. So that's represented by the interval positive 1 up to infinity. And I'm using open parentheses because at 1, my derivative was equal to 0. Last but not least, we're decreasing in between from negative 1 to positive 1. Do we have any relative extrema? Well, it turns out we do. We're going to have a relative max at x equals negative 1, And the reason it occurs at negative 1 is notice that we go from increasing to decreasing at negative 1. We'll have a relative min at x equals positive 1 because I go from decreasing to increasing there. And we'll have no horizontal points of inflection because notice that at every critical point I changed. I either went from increasing to decreasing or vice versa. I never stayed increasing or stayed decreasing. This in total is how you handle one of these problems. Now, one thing that you might see would be if they want your relative max and min to be listed as an xy coordinate. If they did, just make sure you're plugging in negative 1 to my original function. Your original function gives you your y value. On an exam, I probably won't ask for that. However, in the homework, they definitely do. So they're going to want your relative max and min listed as an xy pair, meaning plug these guys, positive 1, negative 1, into your original function to get you your y coordinate that's associated with those points. Let's go ahead and do one more for good measure, then I'll start off with one in class. Let's do g of x equals x to the fourth minus x cubed. All right, since we're after increasing, decreasing maxes and mins and such, we need to find the derivative. And we get 4x cubed minus 3x squared. Now this is a nice enough function. It's never going to not exist. So really we're concerned about where it equals 0 at. In this case, please always try to factor out your greatest common factor. Each term here and here has an x squared in it. So I can pull out an x squared. This leaves me with a 4x from this term and a minus 3 from that term. It's still all equal to 0. Now I set both of them equal to 0. And I get x equals 0. And over here I'll get 4x equals 3. Or that x equals 3/4. And these are my two critical points. What do I do with critical points? Well, I throw them on a number line. So make sure they are in the correct order. I'll throw 0 here and 3/4 here. Draw my little barriers. And then what am I going to do? I'm going to take test points here. Grab a test point for every single interval represented. For instance, over here, I'll pick -1. Between here, I'll pick 1/2. Any point from in here will do. Could have picked 1/4, for instance. And over here, I'll pick +1. And any point from all of this would have done. So you could have picked 2, 5, 27, whatever. Now I'm wanting to test whether I'm increasing or decreasing at the given point. So what I'm going to do is I'm going to plug each of these into my derivative. The derivative tells you about increasing and decreasing. I'll plug into the derivative anytime I need to know about slope, meaning increasing, decreasing. And I'll plug into my original function anytime I need to know about y values. So zooming way up, we'll be plugging it into this right here. When I plug in -1, I'll get -4 minus 3, because -1 cubed is still -1. -1 squared is +1, giving me a -7. So I'm decreasing here. When I plug in 1/2, this one I gotta be a little more careful on. I'll get 4 times. Well, 1/2 cubed is actually 1/8. And I'll do -3 times 1/2 squared, which is 1/4. Well, 4 times 1/8 is just literally 1/2. I'll move this down a little bit. Minus, and that is a minus, I apologize. So we'll have 1/2 minus 3/4, which the moral of the story is it's just negative. That's really the thing we care about. So doing this is actually perfectly acceptable, meaning negative. However, if you want to get your straight up answer, this would be -1/4. So at 1/2, I'm negative, I'm decreasing. Last but not least, if I plug in 1 to my function and go way up to the top, if you need to zoom in and see what it is, notice I'll get 4 minus 3. I'll get +1. So we're increasing here. Now all that's left to do is to interpret. So first off, I think it's helpful, as always, to draw arrows. Notice I'm decreasing, so I'm going downhill. I'm still going downhill over here, and then I go uphill. So first things, let's talk about increasing and decreasing. We're increasing wherever we see a positive, so we'd be increasing on the interval 3/4 up to infinity. And remember, that's kind of why I draw these little barriers. You go from one barrier to the next barrier, all the way that way. I'm going to be decreasing on the interval -infinity up to 0, represented by this stuff. But I'll also be decreasing in between, right in here, right? So I do a little U for union, 0 to 3/4. Notice I do not have any relative maxima, and that's okay, right? I don't have a point where I'm going from increasing to decreasing. I do, though, have a relative min. In particular, we have a relative min at x equals 3/4. I go from decreasing to increasing. And now ultimately we have a horizontal point of inflection. And that's where I went from decreasing to decreasing, which occurred at x equals 0. I could have also had one if I went from increasing to increasing. This down here is my answer in black. Now, by the way, if you did want to get a picture of the function, we actually have a pretty clear picture of what it should look like. And it'll do something like this. So if I draw, you can see where 0 is. Let's say that this is 3/4. We're going to have a graph that does something along the lines of, and then we kind of flatten out because, hey, notice we had a critical point at x equals 0. So I'm flat there. But then, bang, I keep decreasing until 3/4. So notice I'm decreasing and then decreasing some more. At 3/4, I had a relative min, and then I was increasing forevermore. So my graph probably looks something like this if I plug it into a calculator, where the two kind of filled in circles are my critical points, and you can see why they have horizontal tangent lines at those points. We'll do another example as well as talk about what the second derivative means for this picture in next class on Thursday. Thanks for paying attention, y'all. Have a good one.